Hey everyone, just wanted to get what we did in class today down in a video so that you can go back and look and stop and pause as you wish. So this is problem 5.43, the one with the three blocks that are being pushed together, and the push is on block 3 kilogram, and then the block 3 pushes on block 4, and block 4 pushes on block 5, and makes this whole thing move. So it wants to know, the first question is what's the push of 4 on block 5, and right now as you're looking at this problem, there's only one push that we see and we know it. So whenever you're asking about forces on objects, you should always draw a free body diagram. So you see that I have our boxes ready to go as we're here. So the 3 kilogram box has an mg going down, a normal going up. It has a force from the push going to the right. And then remember we talked about how since it's in contact with box 4 is actually pushing back on box 3. So we're going to call this force 4 on 3. Okay, so that's the free body diagram for the third one. We can go, for the 3 kilogram one, we can go to the 4 kilogram one. Again, we have mg down, we have normal up. And in this case, the push itself, the 16 Newton push, is not pushing on the 4 kilogram box, but it's the interaction of the push from box 3, right? So F3 on 4. And then there's also a push happening in the opposite direction of 5, force 5 on 4. Okay, and this is what's responsible for the motion of that one. And then if we go to box 5, mg down, F net up, and in this case there's only one push happening on box 5 because this is a frictionless surface as it told us. Okay, so in this case there's only one force on box 5, and it's the push from 4 on 5. Okay, and the other thing that we know about this unit is that we are always using Newton's second law, F equals ma. So it doesn't matter, like you can apply F equals ma to any object. Okay, you can apply it to 2 objects in a row, you can apply it to 3, you can apply it to 1. So all of these free body diagrams also have an associated F net equals ma. And the question is for us, like, what is the F net? And that's the whole point of the free body diagram, is to figure out the net forces that are involved with our motion. So this says that it moves the things forward. So we're assuming that we have some, it was at rest, so we have some acceleration going to the right. And I'm also going to call the right positive, just to give ourselves a frame of reference, and we can have negative forces and positive forces. So if I'm thinking about this for the Newton's second law for our first object, the mg and the normal force, they cancel each other out. These boxes aren't moving off the table or into the table. So we're only thinking about the forces that are in the horizontal direction. And in this case, it's the push going to the right and the force of 4 on 3 going to the left. And since they are in opposite directions of each other, one is positive and one is negative. Okay, so when we're dealing with F net, this is like grandma giving you $100 and you owing your mom $50, right? So F net is not the 100 from your grandma. It is the combination of the two. One is negative, one is positive. That's exactly what's happening here. And since this object is moving to the right in the positive direction, the push force, right? I'm actually going to just start and remind us that what we are doing is we are doing F net is equal to ma. Right? The net force on this object 1 is equal to the mass of object 1 times the acceleration of the object. And our net force is the push minus F4 on 3. Right? That is the net force, and that is equal to our mass times the acceleration of the box. Okay? Now, if I were to plug in some numbers here, right? We know the push force. We do not know the force of this object, of 4 pushing on 3. We do know the mass of the object, 3 kilograms, but we do not know the acceleration of the object, okay? So this equation does not help us solve for anything. It gives us an idea of what we would need to know in order to solve for things. So we're going to table that one. We can do the same thing with all of these other objects. Okay, again, our motion is in the horizontal direction, so I'm only focusing on the horizontal forces. And again, the mass 4 kilograms is going to move to the right, so when we're doing our net, the F3 on 4 is going to be bigger than F4 on 5. Or sorry, F5 on 4, misspoke. Okay, and again, the reason why I am arranging these as I do is I'm taking into account that my positive force is greater than the negative force. So that's why I'm putting the one that is going to the right in the positive direction and subtracting it from the one that is going in the negative direction. And that's going to be equal to mass times acceleration. And we do not know any of the values of these forces, right? So we can't actually plug anything in here, but I do know the mass, which is 4 kilograms. And again, I don't know the acceleration. So this equation is even more of a dead end because we have 3 unknowns. And if we come over to our last object, again, F net is equal to ma. The only force that is in the direction of motion or in the plane of motion, the horizontal plane, for box 5 is just that F4 on 5. So that's like grandma gives you $100 and you owe nobody nothing. So your net gain is 100. So the net force for object 5 kilograms is just F4 on 5. So box 5 is able to move solely due to the push that 4 is giving to it. And that's equal to mass times acceleration. We do not know that. We do not know the force of 4 on 5. We do know the mass is 5 kilograms. And we do not know the acceleration. Okay, so again, we have a dead-end equation here. And if you're looking at the question, it says, what is the force that the 4, I think it's asking for the 4 kilogram on the 5 kilogram. Anyway, so we could be solving for this, but before I can solve for that, I need to know something about the acceleration. So this is where it comes in handy to be able to think not only about each individual object, but to think about the objects as a system. So I'm going to say all 3 of these objects are acting as one system, right? And we saw this in class. I was pushing the books or the remote or whatever I was pushing in class, and all 3 objects were moving with the same speed at the same acceleration, so they're acting as a system. And that helps us because now, if I draw the free body diagram for the system, oopsies, F normal. And when we're taking into account forces on a system, we only care about the external forces. So the only force that is acting on this system is the push, right? All of these other forces, like the F4 on 3, the F3 on 4, all that, they're inside the system. They start in the system, they end in the system. So we do not care about them when we're thinking about all of our boxes as one system. So if I were to do Newton's second law here, I would say the net force, again, is just the push force equal to the mass times acceleration. Well, I know the push force. And in this case, I have to take the mass of the entire system, which in this case is the 5 plus the 4 plus the 3. So that gives me a mass of 12. And I don't know the acceleration, but now this equation helps me solve for the acceleration. And we said that the acceleration of the system is the acceleration of all of the other objects, right? Each individual object is traveling at that acceleration. So if we solve this equation, we get an acceleration of 1.33 meters per second squared. This is now the acceleration of all objects in the system. And if we're looking at the question, if I can pull it up, it is asking how much force does the 3 kilogram box exert on the 4 kilogram box. So, oh, sorry, my variables are a little different than yours. It's asking for the force of 4 on 5, right? We want to solve for this number. So we're going to use this equation, and now that we solved for the acceleration, right, I can plug in this acceleration to any of these A's in here because all of these A's are in the system that are moving at the same acceleration. So if I want to solve this first question, I would say, I'm just going to keep colors consistent, right? F4 on 5 is equal to 5, because that's the mass of that object, times the acceleration of 1.33. And that gives us a F4 on 5 of 6.65 newtons. Right, so let's think about this. If this box is accelerating with 1.33, right, repeating 3, meters per second, and the box has a mass of 5 kilograms, then this is just like the simplest of our F equals ma, right? And there's only one force acting for the motion of box 5, and that is the push from 4 on 5. So if I know the mass and I know the acceleration, then I have to know that force. The next question is, what force does the 4 kilogram box exert on the 3 kilogram box? And again, we have that in one of these equations. Right? We see F4 on 3. And we knew everything in that equation except for the acceleration, but now that we solved acceleration, we now know that, and we can solve. Right? So we're going to say 16 minus F4 on 3 is equal to our mass times our acceleration that we just got. Now, they are not asking for the net force, right? The net force is taking into account the 16 that is in the opposite direction of the 4 on 3. Okay, we could, right, if we just did 3 times 1.33, and that gave us a value of 3 times 1.33 is 4. Sorry, mental math is not my best at the end of the day. This value right here represents F net, right? And our F net is not just one force, it's 2 forces going against each other. So I'm just plugging in, right? If you want to say that F4 on 3 is 4, well, that doesn't make sense because 16 minus 4 is a net force of 12. And if your net force of 12 is acting on an object that has a mass of 3 kilograms, then your acceleration should be 4 meters per second squared, and it's not. It's 1.33. So we have to use this equation and solve for F4 on 3. So we're going to do 3 times 1.33. We get 4 is equal to F4 on 3 minus 16. So we're going to add 16 to both sides. We get F4 on 3 is equal to 20. Negative F4 on 3 is equal to 20. And now, so in order to actually solve for F4 on 3, it would actually be negative 20 newtons, which makes sense because it has to be in the negative direction, right? Our F4 on 3 is going in the left, which we called negative. So I've said this in class, the math never lies. I should be getting a negative force, so therefore I did get a negative force. Okay. If you have more questions on this, please let me know. Feel free to be pausing and taking note as you will, and we'll talk more in class.